Hello, this is Brian Washburn, and what I'd like to do is give an introduction to the topic of coupled oscillators. Coupled oscillators are very frequently found in physics, both in mechanics and actually outside mechanics. For example, a lot of quantum systems are coupled oscillators. And what I'd like to do is talk about a general method for solving a system of coupled oscillators. To do that, what I want to do is take a look at a problem that we kind of solved before. So in previous homework, we came up with the equations of motion for double pendulums. So what I have is I have two pendulum. They both have a length L and a mass bob M. Okay, so in this case, both pendula have the same length. And then one pendulum, the upper pendulum makes an angle phi1 respect to the vertical, and the second one makes an angle phi2 respect to the vertical. And we came up with equations of motion that describe this. And then in another homework problem, we actually solved those equations numerically. And we saw a very complicated motion. However, under specific initial conditions, we saw very simple motion, something that looked like harmonic motion, and we saw symmetric and antisymmetric motion. And so that's a solution to this double pendulum problem, but it's also a generic solution to any coupled oscillation. So I like to talk about formalism for doing that. Okay, so these are the equations of motion that we derived using Lagrangian formalism, and that's for any angle. So what I want to do is I want to write down a simpler set using the small angle approximation, and I'm still going to get a second order coupled differential equation, but what I'm going to do is using small angle approximation, I'm going to say that cosine of phi, any phi1, phi2 is approximately equal to 1, and then sine phi is approximately equal to phi. That's my small angle approximation. And so if I take that and stick it into these equations of motion, the first equation simplifies a little bit to 2 times phi1 double dot plus phi2 double dot. Then I have 2 omega naught squared sine phi. Now what is omega naught? Well, omega naught is the natural frequency of a single pendulum, and we're going to divide that by G over L, square root of G over L, just like we normally do for a pendulum. Okay. Then we have, that's phi1 minus phi2. Okay. And then notice I have this difference here, so squared, instead of sine, I'm just going to put phi1 minus phi2. Okay. That's one equation. And then the second equation, using the small angle approximations, that comes from the top equation of motion. And then the second looks like this. Phi2 double dot, phi1 double dot, minus phi1 dot times the difference, phi1, phi2, again from the small angle approximation, plus omega naught squared phi2 equals 0. Now those equations still look pretty complicated. Okay, so what also I'm going to do at this point is assume that the angles are small and don't vary with respect to each other too much. So I'm going to assume that phi1 is close to phi2. And then what that's going to do, that's going to drop out these terms that have a difference of phi1, phi2. So they're small and they're close to each other. Okay, so then my equations of motions get a little more simple. I get 2 times phi1 double dot plus phi2 double dot, okay, plus 2 omega naught squared phi1, okay, equals 0. And then the second equation, to simplifying it, phi2 double dot plus phi1 double dot. And then I have just here omega squared phi2. Okay. Again, there's still two coupled second order differential equations. Okay. A little simpler. Okay. However, what I can do is I can write this in matrix formalism, okay? And in the end, what we're going to show is that solving a coupled oscillator problem will be just an eigenvalue problem, all right? So how am I going to do this? Well, what I'm going to do is I'm going to find a column vector. I'm going to call it x. And what is x? X is kind of a generalized coordinate, so I'm going to call that phi1, phi2. That's x, okay? And then x double dot is just going to be equal to phi1 double dot, phi2 double dot. So that's x. And then I can rewrite these equations using these constants. Again, notice there's no masses or lengths because all the masses, m1 equals m2 is m, and L1 equals L2 equals L. And so I can rewrite these equations here in a kind of matrix form, okay? And I'm going to write it like this. So you can see just by 2, 1, 1, 1 times x double dot. Okay. And then I can write this is going to be equal to, and then if I take this stuff here and bring it to the left hand side, I can write minus 2 omega naught squared 0, 0 omega naught squared times x. Okay. Now if you multiply that through and set the top row and the bottom row equal to each other, you will get to these two equations here. Now I'm going to take a leap of faith here, kind of. And so what I'm going to do is I'm going to call that first matrix on the left-hand side, I'm going to call that a matrix M. And so I'm going to make this M and X double dot. And then this matrix here, I'm going to call that, we'll have a minus, I'm going to call that K as a matrix X. Now take a look at that equation there. That equation looks like simple harmonic motion. Remember, in simple harmonic motion for one-dimensional motion, we show that mx double dot is equal to minus kx. That's simple harmonic motion. Here we have an equation that looks like simple harmonic motion, but it's coupled. Okay, all right. So that's what I have. So what I'm going to do is, well, since it looks like simple harmonic motion, why don't I just try a solution of simple harmonic motion and see if that solves the problem. Okay, so, and I want to see if I get some simple equations from that. Okay, so what is my solution going to be? Well, what I'm going to do is I'm going to, so again, I'm going to pick a solution. Well, what I'm going to do is I'm going to pick a, I'm going to say x. Okay, it's going to be a column vector. Okay. And I'm going to say that's going to be the real component of a complex vector z of t. Okay. And what does z of t look like? Z of t looks like, again, it's a column vector a. So I should make, that's a is a vector e to the I omega t. Or really that's equal to, I'm going to call that a1, a2, e to the I omega t. Okay, now if you really want me to think these as column vectors, I'll put a little bar over them or a little vector thing so you know that they're actually column vectors. Okay. All right. So now I'm going to do is I'm going to take that solution there. I'm going to take the second derivative of that guy. And what is that going to be? Well, a is a constant, so that's just going to be equal to minus omega squared. I get that from the second derivative of the exponential a as a column vector, e to the I omega t, but that just equals to minus omega squared z. Okay, and now I'm going to take that z double dot and put it into the above equation. Okay, this equation right here. So again, I'm going to start off with m instead of z double dot k z. Okay, and I'm going to stick this into there and this into there. Okay, now if I do that, what I'm going to get is I'm going to get m, okay, omega squared z, okay, again a column vector, minus k z. Now you can see there, hey, wait a minute, that looks like something times a column vector z equals a constant times a column vector z, where this is a matrix. That's an eigenvalue problem right there. Okay, that's an eigenvalue problem. And so now what I can do is, let's bring everything over on the left-hand side. And so what I can say from there is I can say that k, oops, sorry. Let's get what's right at k minus m omega squared times z is equal to 0. Now the only solutions for that is, so I get the z. Okay, but since I have z's on our side and z has e, I can also write this as k m omega squared a as a column vector. Okay, it doesn't, because z is just equal to the exps on each side just cancel out. Okay. All right. Now, what does that mean? Well, that means that a as a column vector is 0, 0. Well, that's nothing. That's no motion. Okay. Or it means that the determinant of k minus m omega squared is equal to 0. So again, that's an eigenvalue problem right there. So let's find that determinant. Okay, so what I want to do is I want to look at the determinant of k minus m omega squared equal to 0. And I'm going to solve that. Now, again, k and m are 2 by 2 matrices, so what I'm going to get is I'm going to get, let's just write it out. Okay, so I'm going to look at, so the determinant of k, okay, I'm going to write that correctly. The determinant of k minus m omega squared. Okay, let's just write that out. Well, it's k from above is 2 omega naught 0 0 omega naught. That's k minus omega squared. Okay, omega squared is just a constant. I don't know what exactly it is just yet. Those are going to be my eigenvalues, 2, 1, 1, 0. Okay, I'm going to take the determinant of I'm going to subtract those and take the determinant, and okay. And if I will set the determinant equal to 0, I should say. So let's put a 0 here. So 0 is equal to the determinant of that. So that's going to give me the determinant of 2 omega naught squared omega squared. Okay, again, there's a difference between omega and omega naught. Omega naught is the natural frequency of a single pendulum. Omegas are going to be my eigenvalues. Okay, that's what I'm going to be solving for. Okay. Yep. Just looking at it here. Okay. And sorry, there's no naught there. Okay, so that's what I have, and I'm going to set that equal to 0. So if I just multiply that sucker out, what I'm going to get is I'm going to get an equation that looks like I'm going to be 2 omega naught squared minus 2 omega squared quantity times the quantity omega naught squared minus omega, okay, plus omega squared. That's from, so now I get effectively a quartic equation. If you multiply all that through, you get omega to the 4 omega squared omega naught squared plus 2 omega naught squared equals 0. Okay. Now, what you can do is you can write that as a quadratic equation in terms of omega squared, but you can easily, using the quadratic formula, you can find the roots for that. Okay. And I'm going to define, so I'm going to get two values of, technically you get 4, but you get plus minus. So I'm going to get essentially two distinct values. I'm going to call those two distinct values omega s and omega a. And when you do that, you can show that omega s is going to be equal to omega naught, which is the natural frequency of a single pendulum, 2 minus the square root of 2. And then you can show that omega a is equal to omega naught 2 plus the square root of 2. And that comes directly from the quadratic formula. All right. So what are these guys here? They're the eigenvalues of the system. But really what they represent is the frequency of oscillations of the double pendulum system. In the numerical problem, you saw that there were two different frequencies oscillations. There was a symmetric mode and anti-symmetric mode. The S represents symmetric. So this is the frequency of the symmetric mode. That's when the two pendulum move together. This is the frequency of the anti-symmetric mode, where the two pendulum move out of phase with each other. So one motion's in phase, one motion's out of phase. Now we're going to show that in a minute. Okay. So from solving the eigenvalue, you get two fundamental modes of oscillation: a symmetric mode and antisymmetric mode. And one thing, notice that the symmetric mode is always smaller. Okay, so notice we always have this relationship. The symmetric mode is smaller than the antisymmetric mode. But more importantly, the symmetric mode is smaller than the natural frequency, which is the symmetric mode is smaller than natural frequency. However, natural frequency is smaller than the antisymmetric mode. This thing here is a general solution for any coupled oscillator system. We're going to see that quite a bit, and that actually happens in quantum systems. It's pretty cool. So it's very universal. Okay. So now we described the two frequencies of oscillations, but now we haven't really described we know the frequencies, but we don't have something about the motion just yet. All right. So let's now use these results to get the motion. Now really what we're doing in this eigenvalue problem is getting the eigenvectors. The motion actually described by the eigenvectors. Okay, so what I'm going to do is I'm going to pick an eigenvalue. I'm going to say omega is equal to omega s. All right, that's a symmetric motion. And one thing I can also say, motion is simple harmonic motion. So phi1 is going to look like cosine of that motion, that. Okay, and phi2 is also going to look kind of like cosine omega 1 that. Okay, now they might be out of phase, or that part we don't know just yet. What I can do is I can take the second derivative of that. If I take the second derivative of that, I'm going to get minus omega s cosine omega st. Same thing here. I'm going to get the same thing, a minus omega s squared cosine omega st. Okay. So now what I'm going to do is I'm going to stick that back into my equation of motion. Okay, and so if I stick that back into the equation of motion, okay, actually the two equations of motion, okay, what I'm going to get is, so again, what equations of motion am I talking about? I'm talking about these simplified equations of motion. So I'm going to stick those solutions right back into there. Okay, now if I do that, what we're going to get something that looks like, again, I'm going to put omega, so I'm going to put phi1 phi double dot, phi1 double dot, and phi2 double dot. Okay, and if I do that into those two equations, the first equation looks like 2 omega s squared phi1 plus 2 omega naught phi1. Now, in essence, what I'm doing is I'm actually trying to get the eigenvectors. This is just a way of getting the eigenvectors out of this. Okay, that's from the first one. And then the second one is 2 omega naught squared, 2 times, or 2 minus, that's omega. Okay, actually, what I'm going to do, so one thing I would say. So this is, I'm going to use the first equation of motion. And then instead of putting a mech and s, I could use the second one, but actually in the end I could just use only one of them. So this is from this equation here is sticking in the solutions into just this equation. I could have picked that one, but I don't have to. Okay, so let me just do that. And then now what I'm going to do is I'm going to write out omega s. Okay, if I write out omega s, then what I get is I get that plus 2 omega naught phi1. That's the same term I have there. 2 times, and then here I'm going to omega naught squared 2 minus the square root of 2 phi2. Okay, now you can simplify that further, and you can show that there's a relationship between phi2. Phi2 is going to be equal just to the square root plus the square root of phi1. Now, if I set that condition initially, I will get motion of the symmetric oscillation, where the two pendulum are moving with each other. Okay, and in fact, that's exactly what you did in that numerical problem. In the numeric problem, what you did was you picked phi1 to be small. Okay, so phi1 at times t equals 0, you made it, I don't know, pi over 32 or 16, a very small number. And then you set phi2 of 0 as the square root of that. And what did you of that there? And you saw the motion did simple harmonic motion. They were in phase with each other, and they had an oscillation frequency of omega s. That's pretty cool. something that's very complicated, very nonlinear, you found a condition where the motion looked like simple harmonic motion in phase with each other. Okay. Now that's for the symmetric mode. Now you can also do the same thing for the antisymmetric mode. For the antisymmetric mode, what you do is you set omega equal to omega A. Okay. And you basically do the same thing. You, instead of omega S, you just write these things out. You stick them into that same first equation. And what you can show pretty easily just by doing the same kind of math, that omega 2 is equal to minus the square root of 2 omega 1. That means that if you set omega 1, or sorry, phi 1 equals 0, I'll call that pi over 32, then phi 2 is 0 is going to be equal to minus 2 times that. And there you've got an antisymmetric oscillation. However, the oscillation frequency was higher, it was faster. Okay, all right. So the main take-home message from this is that we can take a coupled set of equations, okay, write them in the form of mx double dot equals minus kx, something that looks like simple harmonic motion. We guess a solution that's harmonic, cosines or sines. To make the math easier, we use complex notation. And then the problem reduces down to an eigenvalue problem, where the eigenfrequencies, or the eigenvalues are the normal modes, the normal oscillation modes, and then the eigenvalues are the solutions. Okay, that's the solution. That's our generic. Okay. So let me kind of summarize let me summarize the generic solution to a couple set of oscillators. Okay. So let me write down the general method for solving a system of couple oscillators. So in class, we're going to look at this kind of specific problem where I have two masses, M1, M2, between three springs. In the end, what we're going to show is, and this is just a kind of a picture, but in the end, it could be two pendula, double pendulum, it could be pendulum and a spring, it could be a card and a pendulum, it could be a lot of different things. In the end, we're going to write down the equations of motion, and we can always express the equations of motion in the form of matrix M, x double dot is equal to a matrix K times X. Again, where M is kind of a mass matrix, okay? And if I have two oscillators, it'll be a 2 by 2 matrix. For example, for this particular problem, M will look like M1, 0, 0, M1, 2, okay? The dimensionality of M depends on the number of oscillators. If I have 5 oscillators, it's a 5 by 5 matrix, okay? What is X? Well, X is going to be, well, if you think about each oscillator, each mass has a horizontal position, call that X1, call this one X2. So X is a column vector with X1, X2, like that. X a double dot is a column vector of X1 double dot, X2 double dot. And then what is K? Well, K happens to represent the spring constants. It's a matrix of spring constants. Now we're going to show in class for this particular system, it's going to look like this. K1, X1, sorry, K1, K2, K2, K3. Now what's really important is these off-diagonal terms. The off-diagonal terms are the coupling terms. Now notice that the off-diagonal terms for this one is just K2. If I cut K2, then M1 and M2 will move independently of each other. So it's really the off-diagonal terms is the essence of the physics. It's the coupling. It's the things that couple the couple oscillators. Okay, if you don't have K2, then it's two independent oscillators, and I don't have to do any of this. Okay, we solved that problem. So I can always write this equation of this form here. So how do I solve this? Well, first thing, my methodology is the following. I'm going to assume simple harmonic motion. Okay, so that's solutions, sines or cosines. By assuming simple harmonic motion, I'm going to assume a x, okay, a column vector x of t, okay, all right. That's going to equal to a real part of something called z of t. And the reason why I use complex stuff is because the math is easier. And what is z? Z is going to be equal to, z again is a column vector, okay, which is going to be equal to a column vector A. Well, let's write this one. A1, A2, e to the I omega t. That's the simple harmonic solution. Now, by the way, A1 and A2 are complex. They have to be complex. Remember, if I'm going to solve a second order differential equation, I have to have two unknowns. Okay, so they're going to be complex. In fact, I can write z in general as any complex number can be written as an amplitude and a phase. And those are my two initial conditions, kind of, for what I'm trying to do. Okay, so that's what I'm going to. This is the way your book writes it. Okay. All right, that's step 2. Now what I'm going to do is I'm going to take x and x double dot. So I'm going to take x and x double dot and substitute it into my equation. That looks like m x double dot, or in this case it would be z. So really, again, I'm going to work on, instead of writing x, let me call it z, because I'm going to work as complex numbers, because then it's going to make my life easier. So what I'm going to do is I'm going to take z and z double dot, put it into this thing here, and what that's going to do is, instead of having a differential equation, I'm going to get a linear equation that's in the form of an eigenvalue problem. So what I'm going to get in the end is something that looks like k, okay, minus omega squared m a equals 0. Now the only way that's going to be solution is if the determinant of this is equal to 0. And then my fourth step is going to be find the eigenvalues. The eigenvalues are going to be the normal frequencies. Okay, and then the eigenvectors are going to be the so-called normal modes. All right. So once I've done that, then I've solved the problem. So we're going to do this method we're going to do it on this system here, and you're going to be doing it in homework, but we'll do that in class. We'll see you later. Bye-bye.